Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Welcome everyone. Today we'll dive into the exciting world of sparse autoencoders and their transformative role in large language models. We'll explore how they enhance feature extraction, improve interpretability, and boost scalability. By understanding the power law relationship between compute usage and feature interpretability, we can unlock new avenues for ensuring the safety and reliability of large language models. Let's get started. Can you explain the significance of sparse autoencoders in the context of large language models, particularly in terms of how they contribute to feature extraction and interpretability?
Sparse autoencoders are like treasure hunters for large language models. Imagine a big, messy room filled with toys, where each toy represents a piece of information. A sparse autoencoder helps to find and organize the most important toys, or features, so that they can be easily understood and used. In the context of large language models, sparse autoencoders help to extract clear and interpretable features from all the data these models process. This means that instead of just being a jumble of words or ideas, the model can highlight specific concepts, like famous people or countries, in a way that makes sense to us. The significance of using sparse autoencoders lies in their ability to scale up. They were first tested on smaller models, and there was a worry that they might not work as well on larger ones. But now, they have been successfully applied to a medium-sized model, showing that they can still find and organize important features even in a bigger room of information. Moreover, these features can represent ideas in different languages or formats, like text and images, which makes them even more versatile. This ability to organize and interpret features helps researchers understand how the model works, making it easier to ensure that the model behaves safely and predictably.
What specific methods were employed to train these sparse autoencoders on Claude 3 Sonnet? And how did the scaling laws influence the optimization of their training for feature interpretability?
To train the sparse autoencoders on Claude 3 Sonnet, a specific setup was used. It involved two main parts, the encoder and the decoder. The encoder takes the information from the model and transforms it into a higher dimensional space, sort of like turning a flat drawing into a 3D model. This transformation uses a mathematical process called a linear transformation, followed by a ReLU, nonlinearity, which helps to keep only the most important parts of the information, similar to how a filter might catch only the clean water while letting the dirty stuff pass through. The decoder then tries to rebuild the original information from this higher dimensional rest study, like a sculptor turning a block of stone back into a recognizable shape. Scaling laws played a crucial role in this training process. They are like guidelines that help the team understand how to adjust the size and complexity of the sparse autoencoders for better performance. By following these guidelines, they were able to achieve lower losses during training, which means they were more successful at finding and organizing interpretable features. Thanks to these scaling methods, the sparse autoencoders were able to extract a variety of abstract concepts from Claude 3 Sonnet, helping to reveal how the model behaves in different contexts. This process also allowed for the extraction of features that are not just limited to one language or format, making them more flexible and useful for understanding the model's workings.
What were some of the interpretable features that the sparse autoencoders were able to extract from Claude 3 Sonnet, particularly in terms of their relevance to abstract concepts and safety concerns?
The sparse autoencoders were able to extract a variety of interpretable features from Claude 3 Sonnet, many of which are relevant to abstract concepts and safety concerns. Some examples of these features include 1. Famous people. The autoencoders recognized and categorized information related to well-known individuals, which helps in understanding how the model associates different personalities and their significance. 2. Countries and cities. Features related to geographical locations were also extracted. This is important for recognizing how the model interprets global concepts and the relationships between different places. 3. Type signatures in code. The models learn to track specific patterns in programming code, which is crucial for understanding how the model relates to technical information and can help in ensuring software safety. These features are not only multilingual, meaning they can relate to the same ideas across different languages, but they are also multimodal. This means they can respond to the same concepts in various formats, such as text and images. The diversity of these features and their ability to track abstract behaviors contribute to a better understanding of the model's operations. This understanding is vital for addressing safety concerns, as it allows researchers to see how the model interprets information and make necessary adjustments to ensure it behaves appropriately.
How did the findings regarding the power law relationship between compute usage and feature interpretability impact the overall understanding of sparse autoencoders and their application in large language models?
The findings regarding the power law relationship between compute usage and feature interpretability have deepened the understanding of sparse autoencoders and their application in large language models. This relationship suggests that as more computing power is used, the ability of sparse autoencoders to produce interpretable features improves in a predictable way, much like how more effort in a garden leads to a more vibrant and diverse set of flowers. This systematic relationship indicates that the size of the dictionary, which helps the autoencoders identify and organize features, should be adjusted based on how frequently certain concepts appear. Well, this means that if a concept is very common, a bigger dictionary is necessary to ensure these features are accurately captured and understood. Moreover, the insights gained from this relationship have practical implications. They guide the training process, allowing researchers to optimize the sparse autoencoders effectively. As a result, they can produce clearer and more abstract features that can be interpreted across different languages and formats, enhancing the model's overall interpretability. These findings also underline the importance of efficient algorithms and training methods, as understanding how compute usage impacts feature extraction can lead to more effective approaches. This is particularly relevant for addressing safety concerns, as it equips researchers with the knowledge needed to ensure that AI models behave in predictable and reliable ways.
In what ways do the findings about the relationship between compute usage and feature interpretability influence future research directions in enhancing the safety and reliability of large language models?
The findings about the relationship between compute usage and feature interpretability significantly influence future research directions aimed at enhancing the safety and reliability of large language models. Here are a few ways this impact manifests. 1. Affirmative safety cases. The insights gained from how compute impacts feature interpretability can help researchers develop methods to assess and ensure that models are safe before they are deployed. By understanding the relationship between computing power and the clarity of features, researchers can better analyze whether a model behaves safely in real-world scenarios. 2. Generalization capabilities. Observations that sparse autoencoders can generalize to off-distribution data, such as image activations despite being trained on text, inspire confidence. This ability suggests that future research can focus on enhancing the generalization properties of models, making them more robust and safe across different data types and contexts. 3. Identifying safety-relevant features. The findings encourage the identification of specific features linked to safety risks, such as bias, deception, or harmful outputs. By leveraging the power law relationship, researchers can better understand how to isolate and analyze these features, which helps mitigate risks like biased or dangerous content in model outputs. 4. Efficiency improvements. Understanding how compute affects feature interpretability guides researchers to seek more efficient training methods. This could lead to the development of algorithms that require less computational power to achieve the same or better levels of interpretability, making the process of ensuring safety more feasible. 5. Mechanistic interpretability. The findings motivate further exploration into mechanistic interpretability, where researchers study how specific features influence model behavior. This focus can help bridge the gap between theoretical safety measures and practical implementations. Einstein. Overall, these insights pave the way for a more structured approach to ensuring that large language models are safe and reliable, both during their development and in their application.
Thank you all for joining us today. This discussion has shed light on the transformative role of sparse autoencoders in large language models. Remember, sparse autoencoders enhance feature extraction and interpretability, organizing vital information into clear concepts. They scale effectively, extracting abstract ideas across languages and formats, facilitating model comprehension and safety assurance. The power-law relationship between compute usage and feature interpretability has guided research, leading to advances in safety cases, generalization, safety-relevant feature identification, and efficient training methods. By harnessing this understanding, we empower researchers to enhance the safety of large language models, ensuring their reliable behavior. Let us continue exploring these frontiers, fostering responsible AI development.